Welcome everyone. In this video we will show that an ideal pendulum undergoes a simple harmonic motion under some conditions. Now I'm not saying the conditions right now because I don't want to spoil the excitement of the video. By the end of the video you will see what those conditions are. So let's first start by talking about what we mean by an ideal pendulum. Now, an ideal pendulum is such that all of the mass, which I will denote with m, is at the, let's call it, tip of the pendulum. So, if this is the pendulum, you have the mass here. You treat this object as if it is a point-like particle, and you treat the rope as if it has no mass. Now, a better way to put this is actually that the dimensions of the object here is very small relative to the rope, and the mass of the rope is negligible relative to the mass of the object. So we in fact have a point-like particle that is swinging back and forth, and that we call an ideal pendulum. All right, this is the definition. Now comes the simple harmonic motion part, which I will denote with SHM. What is that? This is the type of motion where the force, the magnitude of the force is proportional with the displacement from the equilibrium, so it is proportional to delta x, and they are oppositely directed, okay? F and delta x are opposite to each other. Now, as a result of this, the equation that the acceleration is equal to a negative constant, which we call negative omega squared, the angular frequency squared, times x. So this is the formula for, excuse me, this is the formula for simple harmonic motion, okay? And we oftentimes write this as dx, so like this. The second time derivative of position should give you negative omega squared times x. If you get this, then you have a simple harmonic motion. And in fact, I derived this in a previous video. You can find that video from the cards right now and also from the descriptions part. Since I have already done this in the past, I'm not gonna go over it in this video. So, for this video, we want to consider the simple pendulum. And there are three ways to approach this problem. One is the force method, the second is the energy method, and the third one is the torque method. And in this video, we will be using the torque method. The torque method. So, for that, let me draw the setup. We have the pendulum at its equilibrium. Then we will pull it to an angle of theta, okay, measured from the vertical. So theta is defined as the angle that the rope makes with the vertical, okay. And this is mass m. This is perhaps length L, the length of the rope, and m is the mass of the object. Point-like object. So if I were to take the torque relative to this point, P, the point where the pendulum is attached to the ceiling, if I take the torque relative to that point, I am considering the mass, so there is mg downwards and there is tension along the rope. Of course, the tension won't be able to create any force because it is along the position vector relative to the point P, right? The sine of 0 or sine of 180 degrees, well, that's just 0. So this doesn't create any torque. There is no perpendicular component of tension. The mg, on the other hand, will create a torque relative to point P. And if I extend this dashed line, I can see that from this Z shape that this angle is theta. And I know that the torque relative to P will be, well, it will be the moment of inertia relative to p times alpha, the angular acceleration. Relative to p, you could say. So the torque relative to p is, you're going to have mg times the moment arm. Moment arm is the length that is perpendicular to the direction of the force. So this is the direction of the force, and this is the moment arm. Its length is, well, this is L, and we have the opposite side, so we have L sine of theta. We're not done for the torque though, because notice that this torque is counterclockwise. Clockwise. And clockwise is defined to be negative, so we put the negative sign here. Now, for the moment of inertia with respect to point P, we said that this is an ideal pendulum, so we have a point-like mass. And what is the moment of inertia of a point particle? It is defined to be the mass times the distance to the axis squared, so L squared for our case, and we have alpha. We see that the mass drops. That's interesting. So the mass of the pendulum bob does not matter. And also the one of the L's will be cancelled. Cool. Now let me write this. Let me write the situation. We have negative g sine of theta equaling L. Instead of alpha, I will write the second time derivative of theta. So d squared theta over dt squared. Cool. And I mean, you might be getting excited. You're saying, okay, we have the second time derivative of theta, but we don't have theta here. We have sine of theta. It will be awesome if we had theta. Then we would be done. And in fact, you can say for small angles, sine of theta is approximately equal to theta. This is called the small angle approximation, and you can check that this holds by using your calculator and make sure that you are using it on the degree, not on degrees, sorry, on radian mode, okay? In degrees, this doesn't make sense, obviously. But if you use radians, this will be correct. And by small angles, we mean, I mean, you can have different opinions on this, but it is around less than 10 degrees, okay? So less than 10 degrees. Even though I give it with degrees to visualize it, please use the calculator on radians, because otherwise you will not get the right answer. And also, this isn't something that you need to accept. I mean, I'm not claiming here that this is correct. I have a video about this. You can access it from the cards right now and also from the descriptions part. And in that video, you can see that this is a result of the linear approximation of sine of x near 0. Okay, so this is not something that we make up. This is, I mean, this can be proved mathematically. That's what I'm trying to say. This is in one of my videos, and I really recommend that you go ahead and watch that video. So then we can, instead of theta, we can write, instead of sine of theta, we can write theta. So we have negative g theta. I should have put approximately equals to, but I'm just going to put equals, okay? And then if we solve for this guy, the angular acceleration, to get it in the SHM form, we get that the second time derivative of theta is equal to negative g over L theta. And we have done it. This is a formula for simple harmonic motion. You can notice that this g over L is the omega squared, the angular frequency squared for this oscillation. And using this idea, you can find the period of this motion, which I plan to do in a future video. So what is the takeaway from this video? Well, the simple harmonic motion can be observed in many cases, like the case for an ideal pendulum. I hope that this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.